Good morning, class. Hi. Okay, so yesterday's homework was from chapter 3. What I need is a shoebox here to hold up the phone. Okay. I gave you the Alka-Seltzer question for homework yesterday. So it says the fizz produced when an Alka-Seltzer tablet is dissolved in water is due to the reaction between sodium bicarbonate and citric acid. Gives you the balanced equation. In a certain experiment, 1 gram of sodium bicarbonate and 1 gram of citric acid are allowed to react. A, which is the limiting reactant? So let's start by writing down the balanced equation. So this class is directed to periods 1 and 2. Now Mamo's trying to play with a wire. So I'm gonna roll it up, or else Mamo's gonna yank the wire and everything's gonna fall off the table. Okay. This is problem number 373. We have 3 sodium bicarbonates reacting with citric acid, which has the formula H3C6H5O7, also aqueous. And the products are as follows: 3 CO2. I don't have enough room, so I have to start here. 3 CO2 gas plus 3 H2O liquid plus Na3C6H5O7. And 1 gram each of those two. 1 gram of sodium bicarbonate and 1 gram of citric acid. So Oh, hi everyone. There's 6 people online. If you could greet me by putting your name so I know who's there. While I find the answer key here. Number 73. Right. So we have 1 gram each in the ingredients. Hi, Ramel. Hi, Stella. Hi, Nancy. Hi, Twinkle. Oh, now we have 7 people online. Hi, Antonella. Moyo Richie. Okay, well, we'll continue. There's 1 gram of sodium bicarbonate and 1 gram of citric acid. So let's find the molar mass of each one of these two, find out how many moles that represents of each one of the 2 substances reacting in the Alka-Seltzer, and we'll find out which one of the 2 ends first. You'll notice also that there's 3 moles of sodium bicarbonate to every 1 mole of citric acid, so we have to also keep that in mind when we do the calculation. So sodium bicarbonate, I'll do that calculation over here. We have 1 gram of the sodium bicarbonate, which is composed of sodium, which is 22.98977 grams per mole, plus the hydrogen, 1.00794, plus the carbon, 12.011, plus 3 times the oxygen, grams per mole. 1 divided this number, whatever that adds up to, is 84, 1.00 grams, divided by 84.00691 grams per mole, means that you have 0.011903783 moles of sodium bicarbonate, NaHCO3. Okay, so we'll do the same calculation for this one over here. So 1 gram divided 8 times the hydrogens. So there's 3 hydrogens and 5 hydrogens. They write it that way because citric acid is it's an organic acid. It has 3 labile protons. It can give off 3 protons under the right pH conditions. Don't worry too much about the structure of it. Just add up the total number of hydrogens, total number of carbons, total number of oxygens. That's all you really care about. So there's 8 hydrogens in this molecule. And 6 carbons and 7 oxygens. So what that equals in the end is 1 gram over 192.125, 32 grams per mole, and that ends up being 0.005204936 moles of citric acid, or H3C6H5O7. So you found the moles of both. Clearly, there's more moles of sodium bicarb. There's 0.005 of this, and there's 0.011 of this one. But remember, you need 3 times as many moles of sodium bicarb as you do of citric acid. So we're going to find out which one runs out first. I'm thinking that citric acid is going to, no, sorry, because you need 3 times as many moles of sodium bicarb, I'm thinking this is going to run out first anyway. So we'll just remember these 2 numbers. I have to erase because there's no more room to write on this postage stamp of a board. So we start off with 5.204 936 times 10 to the minus 3 moles of citric acid, H3C6 H5O7, times 3 moles of sodium bicarb, NaHCl3, for every 1 mole of citric acid. Allows me to cancel citric acid. 3 times this number gives you 0.015 614 808 moles of sodium bicarb needed. Well, let's compare it to what we already have. We only have .0.011903783 moles of sodium bicarb, which we can rewrite in exponential form if you want. You can move that decimal over twice. We get 1.1903783 times 10 to the minus 12 moles sodium bicarb. Now let's just subtract this number from that number, and we'll see how much is going to be left over. Actually, we're not asked that yet. We're not asked that quite yet. We're just being asked which one is going to run out first. So we need that many moles. We need that many moles, which is equal to 1.5614808 times 10 to the minus 2. But this is how much we have. So we actually need more moles than we have. So the limiting reactant is, in fact, the sodium bicarbonate. What I wrote in the answers is roughly 0.015 moles of sodium bicarbonate is needed, but only 0.0119 is 0.011 is available, so it's going to run out. The NaHCl3 is limiting. Part B is asking how many grams of carbon dioxide form. The number of grams of carbon dioxide that forms is equivalent to the number of moles of sodium bicarb that was present. And what's present is this one. So we're going to continue the calculation by saying 0.0119 0.3 783 moles of sodium bicarb times 3 moles of CO2 is produced for every 3 moles of sodium bicarb present. That allows us to cancel moles of sodium bicarb. So what we're going to get is that many moles essentially, because 3 over 3 is 1. So you get the same number of moles of CO2 generated as you had of the sodium bicarb in the beginning of the reaction. Multiply that by the molar mass of carbon dioxide, which is 44.0098 grams per mole, and you were going to get the answer is 0.524 grams of CO2 after sig figs, obviously. You should see how much snow there is here today. Have a look. There's about 4 or 5 inches of snow. It was snowing all day yesterday. We're not finished the question. We've only done part B. Hey, Mama. Good Mama. Hey, Mama. How are you, buddy? Okay. Not too happy, are you? What do you want? He's looking at me. You want food? The next part is they ask you how much citric acid is left at the end. How many grams of the excess reactant remain after the limiting reactant is completely consumed. So again, you have to keep in mind that the stoichiometry is 3 to 1, like I said, like I wrote in the first board. Hopefully you still have that written in your notes. Hopefully you wrote some notes. So first to find out how many moles of the citric acid is used. Okay, we gotta make room again. So you start off with 0.011903783. Now I'm struggling to read my paper. This is the missing part here. So you have that many moles of sodium bicarb, and you're going to get 1 mole of citric acid for every 3 moles of sodium bicarb that's used, which means you're going to use up 0.003 and 967928 moles of citric acid. Now, some of you are going to have something else show up in your calculators. I'm just going to show you what it looks like, although you should know how to do that to convert between a decimal and a scientific notation. Just move that decimal over 1, 2, 3 times. So on your calculator readout, it's probably going to look like this: 3.967 9 to 8 times 10 to the minus 3. So if you got that, you're okay. You're not getting a different answer. You're on the right track. So that's how many moles of citric acid is going to be used. What you originally had was what you originally had was 0.0052 04936. You're going to use that much, or that much, whichever one you like to write. What's going to be left is this much, 0.0012 37008 moles of citric acid left. Multiply that by the molar mass of citric acid, which you calculated earlier in the problem. So you're going to multiply that by 192.12532 grams per mole. And what you get is that there are, at the end, there are 0.237660622 grams of citric acid left. Wait a second, I think I may have written something down wrong. No, the excess is the citric acid. Yeah. So basically 0.2, you're only about 3 sig figs, so you say 0.238 grams as your final answer. Okay, anybody get that one? It's not hard in any of its individual steps. There's just a lot of steps, but you just have to keep the numbers straight. Sometimes it helps. Look what I did in my notes. I put what I have, what I use. So it doesn't hurt to throw a little note to yourself so that you understand what each of the numbers are, because it's easy to lose track of what you're doing if you don't keep track of everything, especially when you're struggling to understand what the steps of the calculation are. So write yourself a little note as you go through it. Annotate your problem. It can help you solve it. Now, I don't know where you guys are standing in terms of the 80 questions I gave you. I think, given the circumstances, it's probably a very good idea for you to go through the whole chapter and use that as your practice. I think you would learn more doing that than actually attending class. But you should do both, of course. We're essentially at the end of the chapter, as far as I'm concerned. And 105. It's a good question to try because it has a percentage in it. Let's read the question and attempt it. It says on question 104, no, sorry, 105. It says a particular coal contains 2.5% sulfur by mass. When this coal is burned, the sulfur is converted into sulfur dioxide gas. The sulfur dioxide reacts with calcium oxide to form solid calcium sulfide. A, write the balanced chemical equation for the reaction. B, if the coal is burned in a power plant that uses 2,000 tons of coal per day, what is the daily production of calcium sulfite? So the first challenge of this problem is to figure out what the equation is. It doesn't give you an equation, but you can, if you know your polyatomic ions by heart, it shouldn't be too hard to write. So you have sulfur dioxide gas reacting with calcium oxide, which is a solid, to yield calcium sulfate. I'm going to use metric tons. Metric tons is 1,000 kilograms. Americans sometimes use short tons, which is just 2,000 pounds. So the answer at the back of the book is in short tons. I did the calculation in metric tons. But you know, this is an American book. Americans still use their old system when they can. So 2,000 metric tons times 25 1,000ths. Why am I multiplying by 25 1,000ths? Because 2.5% sulfur is 25 1,000ths. It's 2.5 over 100, or you could say 25 over 1,000. So that means out of those 2,000 tons of coal, what you have is 50 tons of sulfur times 1,000 kilograms per 1 ton times 1,000 grams per kilogram equals 5.0 times 10 to the 7 grams of sulfur. Now, if you have 50 million grams of sulfur divided by the molar mass of sulfur, you're going to get 1.559, 283, 98 times 10 to the power of 6 moles of sulfur. And because the stoichiometry is such that you get, for every mole of sulfur, you get a mole of sulfur dioxide, and you cannot get also the same number of moles of calcium sulfate because it's 1-to-1 ratio. So you can write S, SO2, and CaSO3. So you're going to get the same moles, same number of moles for all three of those substances. And the end result is that you simply calculate how many grams of calcium sulfate you're going to get. So if you get that many moles of calcium sulfate, multiply by the molar mass of calcium sulfate, which is 40.078, plus 32.066, that's the sulfur part, plus 3 times 15.394, that's the oxygen part. So what you get is 1.87, 335, 807 times 10 to the 8 grams of calcium sulfate. Or if you like, put that up here again. You got 1 ton per 10 to the 6 grams. So you got 187 tons. You're only allowed 2 sig figs. So really you'll have to report 190 tons as your final answer because that's only 2 sig figs. You know what, guys? I'm going to stop it there for today because I don't want to overload you on the first couple days back. Why don't you try something? See how good you are. Try problem number 100 tonight. See if you can do problem 100 for homework. Okay. Usual conditions apply. If you get me the answer, but I'd like to see, I don't know if you can send a picture in the comments. Try that. See, show me a picture in the comments that you can do all the steps of problem number 100. and I'll give you a bonus on your final exam, okay? All right. I'll talk to you tomorrow.